what we're going to do now is we're going to take an example I used earlier in conservation of energy, and I'm going to end up adding in a component for friction. So let's do the same thing. If a car V equals 2 meters per second, traveling rolls down a 4 meter high hill, 4 meter high, 80 meter long hill, what is, if the final velocity is 7 meters per second, what is the friction force? So there's actually multiple steps in a problem like this. It's still a nice little problem, but so again we draw a picture. So we've got a hill, car up the top of the hill, and it rolls down the hill, down the bottom. So up the top, the inertial is going to equal what's going to be, there's going to be potential energy plus kinetic energy, and down the bottom E final is going to equal E kinetic. So let's work out how much energy there is at the start. So write down what we know. VI equals 2 meters per second, VF equals 7 meters per second. What else do we know? H, the height of the hill, is 4 meters, and we know the length of the hill, which will become important later, is 80 meters. Now, so we work out the initial energy. E initial is going to equal EP plus EK, which is going to equal, EP is going to be mass times gravity times height plus half mv squared. We can do this all in one hit. So it's going to equal, what did we say, mass is 1200 kg. 1200 kg times 10 meters per second squared times 4 meters plus half M is 1200 kg times velocity squared, up the top is 2 meters per second squared, and we worked this out in the previous example to be 50,400 joules. So at the top, 400 joules. What's the final energy going to be? The final energy is equal to EK, which is equal to half mv squared, final velocity squared, which is equal to half 1200 kg times the velocity, we said is 7 meters per second at the end, square, and we square that, so that's going to equal half 1200 times 7 squared equals 29,400 joules. Hold on, something's gone interesting here. We started with that, we ended up with that, so we've suddenly lost 21,000 joules of energy. But according to conservation of energy, we should have the same energy. What happened to that energy? The answer is, energy can't be created or destroyed, but it can be changed from one form into another. In this case, we had friction, and friction will produce heat, as a rule, will produce heat energy, and sometimes sound energy and a bit of light energy. So, what we actually have is we end up with the final equals 29,400 So what's the change in energy? The change in energy is going to equal the final energy minus the initial energy, which is equal to 50,400 joules minus 29,400 joules equals 21,000 joules. 21,000 joules. And we actually have a special name for change in energy. Change in energy is also called work. So the work done in this case is 21,000 joules. And that work is actually done by friction. We actually have a friction force, which is opposing the motion all the way across there. So how can we work out how big that friction force is? Well, we know what the work is. Work is equal to change in energy, but work in a mechanical sense only is equal to force times distance. So if I rearrange this, force, that's what I'm after, force is equal to the change in energy over the distance. So if we divide that by the distance, 80 metres, that will tell us what the friction is. 21,000 joules over 80 metres equals 21,000 divided by 80. 262.5 newtons of force. So friction force equals 262.5 newtons. So often we will do problems like this where we work out the energy at the top, the energy at the bottom, and if they're different it's because there's friction. And friction force, the friction force chews up energy in the form of work.